Okay, this video is 3C part 2, so this is the second half of the introduction to matrices. So this video is solely focused on the multiplication of matrices. Now again, I want to illustrate the last video we watched is combining data through addition. So you're literally adding like one class to another. But now if we want to find the product of something, we have to take one data, multiply it by something, and then you get end result. So later on in the chapter we'll talk about how to solve such things, but what I want to do is open up with the original question. So this is the first slide we saw of how to solve longhand algebra, three equations with three variables. Okay, so we've seen algebra wise. The last video I showed you how to organize the data. So what we have here is simply the organization of the data. So there's the three equations. Notice the matrices of the coefficients, then we have the matrix of the variables, and then we have the totals of the equations. So what I want to do is just kind of reverse it and show you, okay, how do we take this data and produce these answers? So let's go ahead and highlight something here. So if we want to create, let's say, the first equation, I'm going to highlight it in green, okay? And we want to get these three terms in standard form that produce a grand total. So let's look to see how it happens. All right, so the first term is 4 times x, okay? And so let's go ahead and, well, let me highlight them first. And then the second term is going to be 5 times y. And then the third term is going to be 3 times z. And what do they produce? 15. Okay, so what I want to do is highlight, how this process works. Now notice we talked about labels before. We want this variable and this variable to cancel. Just like if we take something feet and we want to get rid of feet, we put feet on the bottom and inches on top. You put them in opposite positions, so rows and columns are opposite and they cancel each other out. Okay, so let's take a look here. So how do we understand how to get this answer? Well, this position right here, these are called rows and this is columns. And again, everything is ordered by rows and then columns. I always like to think of RC Cola. So here we have row 1, column 1, row 2, column 1, row 3, column 1. So call this row 1, row 2, row 3, and column 1. Over here we have, again, row 1, row 2, row 3, and then column 1, column 2, column 3. Okay, and likewise over here. Okay, so to get this position, this is row 1, column 1. So when I look at the data, I take row 1, R always comes first, and then column 1, and I combine those two data by multiplication. So let's go ahead and do it. And you do it piece by piece. 4 times x is 4x, and then you add the next set of terms. The second entry, 5 times y is 5y. And then you add the next entry, 3 times z is 3z. And notice when I write this, and what does this grand total equal? 15. And notice that is the exact same algebra statement we started with. So that's the, a lot of students ask, well, why is it a row over here and a column over here? Well, we want them to connect and the labels cancel out, and then you get a product of the sum. Okay, so what I'm going to show you is a bunch of examples of this, the mathematics behind it, and we'll come back to this example at the end of the video and show it again. In this slide here, we're going to show you how to, by hand, go through a multiply matrices. Now, let's talk a little bit about notation. What we see here are capital letters. These capital letters represent matrices. So this is basically like matrix A, and again, matrix or in brackets. What the capital A represents the whole set of data times matrix B. So that's what that represented there. So just like variables, the capital variables in matrix notation means it's representing the whole set of data. So that way we can kind of go through the algebra of all the data, and then at the very end, the calculator will calculate it all. So that will equal a product, and then you can call it a new matrix, like matrix C if you wanted to. But again, we're showing it as a product of A times B. Now, this is completely different than if I took B times A. This would be a completely different set of data, because the labels would not match. So we'll talk about that more in class and different types of problems and so forth. So the key thing is that that's different. So I'm just going to put a little note there for that. Okay. Now, in all matrix things, when we name them, it's always row times column. So row times column. Okay. And I always like to think of it as RC Cola. Okay, R before C. So whenever I say something, we'd say matrix A is, for instance, row times column, row times column. And the key is we want those two middle things to cancel out. We want this set of columns to cancel with this set of rows. Those have to be identical. Okay, and we're going to see that later on when we solve problems and you see units. But right now this slide is showing, how to by hand go through the computation here. Okay, so what we're going to do is, okay, so if we want to multiply these, and so the first thing I have to do is, okay, right, what we have here is a 2 by 2. We have 2 rows by 2 columns, and over here we have 2 rows by 2 columns. And again, I'm looking for that these two are the same, so they're going to cancel each other out. So then we have the original 2 rows, and those end up over here. And then we have the last 2 columns, which are right here, and those end up right here. Okay, and notice these get canceled out. So I'm just going to go ahead and just scribble those out for right now to show you. Okay, now that's what happens. I'm going to erase them so we kind of see what's going on. Now, what we want to do is, how do we get our final product? So our final product is a 2 by 2. So over here we have a 2 by 2. So notice we have 4 entries. We have this entry, this entry, this entry, and this entry. This number is representative of row 1, column 1. So when we look at RC code, it's always row, then column. So in the first matrix, we are only concerned with the first row. And in the second matrix, the first column. So we're going to take this row times that column to get this sum over here. So let's just kind of show how that works. Now, what I'm going to do is just kind of show you what we have. So basically we have A first entry times first entry, A times E, A times E. And then you add it to the next entry. Next entry is B times G. When we multiply this and you add it together, you get a final number, and that's the data entry point that represents row 1 times column 1. Okay, so let's go ahead and move to, for instance, row 1, column 2. So I want to look at row 1, now column 2. So this data represents A times F plus B times H. First entry and then second entry. And notice right here, AF, BH. Okay, let's go ahead and look at column 1 and then row 2. So again, I'm going to move this down to row 2, rows first, and then column 1. First entry is C and E. There's the C and E. Second entry is D and G. D and G. You get a final product here and final sum and put it right there. And then the last one obviously is row 2, column 2. So I just move this over and look at first entry C and F. We can see it right here. And then D and H, see it right here. Okay, so that kind of goes through the longhand how to do this. And again, it's very important to know why this works, because when we set up with a calculator, we have to set up the problems to make sure that this process happens. So the next slide will show you examples of this. All right, so let's take a look here. So when I look at this thing here, the first thing I have to look at is, okay, are these two the same? Do they cancel out? Yes, they do. And your answer is a 2 by 2 matrix. Okay, so let's find this position right here. That's row 1, column 2. Row 1, column 2. 4 times 2 is -8, and then I'm going to add it to -5 times 1 is -5. You add -8 and 5, and you should get -13. And we simply do that for all 4 positions. Let me do this one over here. So first I'm going to make sure that those are the same. They are. Cancel out. Final product is a 3 by 2. And let's find this position, which is row 2, column 1. Row 2, column 1. So notice I'm literally drawing circles on the problem. So really get organized doing this. So I'm going to start with first entry, -2, 2, so -4. Add next entry, 5, -3, -15. Add those together, -19. Okay, and here we can see more examples here. Now notice this one we can't do because the 2 and the 3 don't match. Okay, so it can't be done because the column and rows don't cancel each other out. Now here's a great example over here. We have a 3 by 1, 3 rows, 1 column, 1 row, 3 columns. So then notice the 1s cancel each other out, and we have a final answer 3 by 3. So let's go this entry right here. That's row 2, column 3. Row 2, column 3. Multiply those two. 2 times -2, -4. Simple entry. Okay. So we'll talk more about, what types of problems that would generate such data. But in this video, we're talking about how can we multiply the data. Let's take a look at some more examples here. All right, so this goes back to the original piece. Okay, so let's go ahead and do the second equation, show where this comes from. So this is row 2, column 1. Row 2, column 1. So 1 times x, 1x. Next entry, negative 3 times y, negative 3y. Next entry, 2 times z, 2 times z. And the final product is, again, row 2, column 1 equals negative 6. And again, that is producing the algebra statement that we see right here, known as the exact same equation. So this purpose of this matrix is to show how we can take algebra, a system of algebra, translate it to matrix, and understand how it works, and then likewise, how do we take a matrix and translate it back to algebra. Okay, so really that's the kind of purpose of this video here. We'll talk more about that, but this video is really focused on multiplying. And again, this is different than adding, two totally different operations. Later, future videos, we'll talk about the applications of it and really try to understand how to set these up and use matrix to make math easier, which is always a big fan of everybody. Okay?